Okay, thanks for the invitation. Practical things, there are some notes available at that website. They are almost certainly full of typos, so that is left as an exercise to the readers to spot. The rough outline for what I was hoping to talk about is topological solitons. Today, just giving some background independent of cosmology. Then tomorrow, talk about their possible role in cosmology. Then non-topological solitons, possibly vacuum decay, and maybe some realizations of the first four things that I'll mostly talk about in the context of weakly coupled scalar fields and similar kind of theories in perhaps more realistic, strongly coupled theories. But of course, it doesn't actually matter whether I get to the end of these things, so please do interrupt me at any point. I'm happy to discuss things in more detail, answer questions, and so on. By way of a quick introduction, why are we doing any of this? Well, of course, we all know that the Standard Model is not the end of the story for fundamental particle physics, and indeed it cannot even account for the cold dark matter that is a part of the Lambda CDM, Standard Cosmological History. And we'd like to discover new physics, of course. Partly this is just because we'd like to know what the new physics is. It's kind of interesting what dark matter is, but also with the hope that maybe if we discover new physics, it would give us some insight into some more fundamental principles, string theory, or similar things. Of course, one route to discovering new physics is particle colliders. You all know this very well. These tend to be spectacularly sensitive to new physics at, say, scales of the TeV scale or less that are relatively strongly coupled to the Standard Model. Of course, it doesn't actually have to be the strong interactions, but at least have some pretty sizable interactions. Alternatively, you could discover indirectly new physics up to higher energy scales, but you have to rely on something like flavor changing effects, strong CP violation, or similar. On the other hand, we're going to consider the possibility that we could discover new physics by early universe cosmology. Or perhaps astrophysics at late times. Compared to particle colliders, we'll see that early universe cosmology potentially gives us access to new physics at much higher energy scales. If, for example, we're looking for direct signals of gravitational waves produced at very early times. Alternatively, it could also give us access to new physics that is very weakly coupled to the Standard Model. Not weakly coupled, but much, much more weakly coupled. It could also potentially give us predictions for like dark matter scenarios, insight into how to search for new physics that way. And just to say some terminology, if I talk about a hidden sector, I just mean some set of new particles and interactions that are interacting among themselves relatively strongly, but interact with the Standard Model only extremely weakly, perhaps only by gravity. We're, as given by the title, also going to talk about non-perturbative physics. And of course, in some sense, this is a bit of a, let's say, blurry definition, because in many of the examples, to actually do computations, we're going to need some small parameter. But for my purposes, beyond non-perturbative physics just means anything other than the usual quantum field theory about a flat space-time independent background. Okay. I'm talking mostly about non-perturbative beyond Standard Model because this was the title I was given. This isn't to say that perturbative aspects aren't equally important. Of course they are. You'll probably see many examples in your other lectures in this school. And also just to emphasize, the topics presented are mostly just a matter of taste and what I think fits reasonably well together for 5 lectures. It's not necessarily meant to be a judgment of their importance. And finally, just as a kind of disclaimer, as the last part of the introduction, there's no guarantee that anything that I will talk about in this set of lectures is realized in the actual universe, unfortunately. It would be very nice if some of them are. As some sort of way to counteract this, as you'll see, I've tried to cover a few different topics, hopefully increasing the odds that some of this will actually be relevant. Of course, that comes at the expense of covering one topic in depth, so there'll be various places where I leave calculations to you, and if you look in the notes, there's many more references where you can also see the original literature and read things in more detail. Okay, with that said, on to some actual physics. Okay, so topological solitons. The idea here is that if we have spontaneous breaking of some symmetry, this typically or often leads to dynamical objects that are extended field configurations. In many cases, these dynamical objects can be rendered stable by virtue of having particular boundary conditions, as we'll see in great detail, or due to some other aspect of their topology, in which case we call them topological solitons. Maybe the main thing to emphasize about these states is that they are not small fluctuations around the usual space-time independent vacuum. Instead, they are really some extended states that should be thought of as the building block of another section of the Hilbert space. Maybe one way to think about them is as bound states of infinitely many of the usual particles. And another key feature that we'll often see in examples is that they tend to be, or actually in general, are singular in the limit of infinitely weak coupling, which tells us that they're not accessible in perturbation theory. So, to see this in more detail, we'll start with a warm-up example, which is domain walls. Let me consider a theory of just a single real scalar, really the most simple thing I could imagine. And let me consider just the simplest spontaneous symmetry breaking potential that you could imagine. I'm sure you will have all seen this in great detail many times before, such that the Z2 symmetry of this underlying theory is spontaneously broken by the vacuum. Then it's completely plausible, indeed, that there are field configurations such that if I look at the universe, on one side of the universe, the theory is in one vacuum. Let me say phi is equal to, maybe minus v is nicer, minus v over there. Whereas in the other side of the universe is in the other vacuum. Then, since we restrict ourselves to field configurations that have finite energy density, this boundary must be some smooth interpolation between the two vacua. Yeah. Sorry. Thank you. Okay, to study these configurations, let me fix the space dimension d to be equal to 1. In general, it's useful to think in terms of different numbers of space-time dimensions. I'll call this total space-time dimension d plus 1. D, of course, is the space dimensions. And then let me define what I will call a superpotential. For people who have studied supersymmetry, it'll be very obvious why this is called a superpotential. For anyone who hasn't, it's just a name, so it doesn't matter. W to be equal to g over root 2, third, phi cubed, v squared phi, which is such that the potential U is is equal to half dw by d phi squared. Now with this, I can write the energy of a static configuration, E, to be equal to integral dx. Since I'm considering a static configuration, of course, there's no time derivative. So then all I have is that I have a half d phi by dx plus your phi. And now I do a small trick that actually appears all over the place when studying topological solitons. I write this as integral dx half d phi by dx. Then I have the choice of a plus or minus sign, dw by d phi squared. And now if you stare at this final term, it's integrated over x, so you can convince yourself that this is equal to minus or plus the superpotential evaluated on phi at infinity minus the superpotential evaluated on phi at minus infinity. At this stage, we've actually got somewhere. This first term is positive definite, whereas this second term depends only on the boundary conditions. As a result, the lowest energy field configuration that has particular boundary conditions, for example, with the universe in minus v at the left of the board and plus v at the far right of the board, must satisfy d phi by dx. Here, with the way that I've chosen my boundary conditions up there, I'm going to pick the plus sign here because I want to get a lower bound on the energy. That means I get the minus sign here, so I need d phi by dx is equal to dw by d phi. So if I can solve this first order equation, I can find the field profile that satisfies these given boundary conditions. It's also worth noting that if I do satisfy that equation, then I get a field profile out that automatically satisfies the equations of motion. If I just differentiate both sides with respect to x, I get d squared phi by dx squared is equal to d squared w by d phi dx. And after a few lines of algebra, you get that this is equal to du by d phi, which is the equation of motion. For the particular potential that I wrote up there, wherever it was there, these equations are easy to solve. The solution looks like phi, and I'll call this domain wall of x tanh. And if you plot this solution, of course, it looks like you'd expect. It starts from minus v at minus infinity and transitions to plus v. All of this is straightforward, but there's a few things worth pointing out that appear more generally. So we have this parameter x0, which appears actually as a constant of integration from the solution. This labels where the center of the domain wall is. So in general, actually, we have a whole family of domain wall solutions at different positions. This x0 is kind of like a collective coordinate, or in some cases it gets called a modulus. Since we're working in one space dimension, the domain wall solution has an energy that is localized. It has actually exponentially little energy away from this point x0. And it has a thickness, you can immediately see from this, that goes like 1 over g times v. Actually, let me leave that up. Meanwhile, the total energy of this domain wall, just its mass, we can immediately see from the formula up there, is just equal to W phi plus minus where I've just called phi at plus infinity phi plus, which is pretty much going around in a circle. Integral d phi dw by d phi maybe it's useful also to write these expressions in terms of the mass of the single particle excitations around each of the two vacua. These have masses of just v times g. So let me say that lowercase m is v times g. Then for this particular example, we have that the mass of the domain wall goes as, forget the order 1 factors, g times v cubed goes as m cubed over g squared. So indeed, as we kind of anticipated already, in the limit of small coupling, the domain wall becomes arbitrarily heavy compared to the mass of the elementary excitations. Actually, this limit of weak coupling is also exactly the classical limit, where we can treat the domain wall as some classical object in the full quantum field theory, around which there can be small fluctuations. Okay, so we've proved that such a field configuration exists. The next question is it stable? In some ways, this is already intuitively obvious. If I have any small fluctuations around this solution, then clearly they can only increase the energy because of this argument above. More generally, if I imagine also large fluctuations, you can see that if I wanted to get rid of this object completely and move it down to some small fluctuations around the space-time independent vacuum, I would need to simultaneously move the field all the way out here in space down to this vacuum. A more precise way to state this is to introduce a conserved current, topological current to be precise. So if I define J mu to be equal to minus epsilon mu nu d nu w of phi, then you can immediately see that d mu j mu is equal to 0 identically. In fact, this is true on any field configuration, unlike a normal Noether current. This isn't true just on the equations of motion. It's just identically true from the definition. Then the conserved charge is just integral dx j0, let me say from minus infinity to infinity, is equal to up to minus signs plus this expression. Okay, so from this. Yep. Okay, so we know this current is conserved. We know the current is conserved. That means the corresponding charge is conserved. So then if the domain wall is the lowest energy solution with a given charge, we'll see. So indeed we can, but yeah, good question. We can immediately see that the domain wall does indeed carry this charge Q because it has non-zero value of this thing. That means that the lowest energy field configuration with a given Q must be stable because there's no way to get rid of this charge. Actually, it also means that the lowest energy configuration with a given charge has to be at least a local minimum of the set of all possible field configurations, which is again another way to see why the domain wall solution was always going to solve the equations of motion for us. Then to maybe say some obvious things, there of course also exists an anti-domain wall solution, which interpolates in the opposite direction between the two vacua. This carries exactly the opposite charge to the domain wall. So then, just like Pratik was talking about instant-on and anti-instant-on field configurations, I could, for example, imagine a configuration that has a domain wall over there, then an anti-domain wall over here in space. This now contains, or this field configuration has zero topological charge Q, so it's not stable. And indeed, if you wait a sufficiently long time, this domain wall and the anti-domain wall will attract each other and annihilate away. This takes exponentially long, at least for this domain wall solution, because the field profile gets arbitrarily close to the vacuum in between them. Okay, good. So, sorry, do this. Okay, so just to anticipate what comes next, we can see that this domain wall solution arises because the vacuum manifold of the theory, by which I mean the set of scalar fields values that minimize the potential, is non-trivial. In general, I'll call the vacuum manifold curly M. In this case, this is just the set minus V plus V. If we want to be mathematical about this, we can say that this is due to the zeroth homotopy group, pi naught of M being non-trivial. For people who haven't come across it, the zeroth homotopy group just counts the number of disconnected components of a manifold. Actually, it's not even a group, and I think it's less intuitive to define than the higher order or the higher homotopy groups, so don't worry if you haven't seen that before. I'll give better explanations of the later ones. So of course, now that I've got my domain wall solution in one space dimension, I can embed it into higher space dimensions. So for example, just as I drew in the first place for a 2D universe, I can have a domain wall like that. For a three-dimensional universe, it's a sheet, and so on. In these situations, the domain walls, at least in an infinite universe, the domain walls no longer have finite energy. What they have is finite energy density. But maybe we're also happy with field configurations that have infinite energy as long as the local energy density is finite. Maybe the only things to point out in higher dimensions is that a single infinitely large domain wall is topologically stable in the same way that it is in one dimensions. On the other hand, I can also construct metastable domain walls that consist of, say in 2 dimensions, a large topologically trivial closed domain wall. In this case, the domain wall can shrink down away to nothing. It carries no topological charge. But if it's sufficiently large, it will take a long time to decay away. One useful and potentially very important example for Pheno is the axion. So as you'll hear in more detail, probably in the other lectures, if I consider an axion A with some potential of the form ma squared fa squared 1 minus cos, let me call this n domain wall, a over fa. So ma and fa are just parameters, n wall is some integer. Then if we have, n wall greater than 1, you can immediately see that this potential will have domain wall solutions. For example, interpolating between the n wall different vacua. Something that sometimes gets glossed over is that also there are domain wall solutions even for n wall is equal to 1. In this case, the potential, if I say look at the cosine down, has a single minimum, say at a is equal to 0. You may think, based on this counting argument with pi 0 of m, that there would be no domain wall solutions, but actually there are domain wall solutions. These correspond to winding the whole way around the vacuum manifold and ending up back at the same vacuum. So despite the fact that in this case we only have one vacuum, we still have topologically stable domain walls. Okay. I think probably in order, given time, I will skip the further details of domain walls. Maybe I'll just very briefly say that if you want to study, say, the quantum theory of this potential of the real scalar field, and you want to quantize the excitations around your domain wall solution, then you can do so. The way you do this is I write my field as the domain wall solution plus some small fluctuations around it. Then if you work out your Hamiltonian as the form dx chi dot squared t. But then instead of just having some usual spatial gradients and mass terms at quadratic order in the fluctuations, we now have this operator L2. And actually, when you go through some algebra, you get that it's equal to this expression evaluated on the domain wall solution. As a result, we get some spectrum of the fluctuations around our domain wall solution that satisfy O2 of chi is equal to omega n squared chi. The one thing that actually does matter quite a lot for the quantization of this theory. So there's omega double prime, where prime is d omega by d phi squared, then omega prime, omega triple prime. There's a few lines of algebra to get to this. Yeah. So a key thing about this analysis is that there's one zero mode omega 0 is equal to 0. And this corresponds to spatial translations of the domain wall. So it costs no energy to fluctuate the domain wall in one direction, keeping its profile otherwise the same. This makes the quantization of somewhat subtle. You need to be a bit careful to separate out this collective coordinate that I mentioned before. And then in addition to this, there are, I think, in this case, one or maybe two bound states with omega n less than the mass of the fundamental excitations. These are fluctuations that are sort of bound to the domain wall. And then in addition to this, you have a continuum of solutions with omega n greater than m, which are just like the domain wall solution with particles unbound to it. And then with that, you quantize your theory as usual. Okay. Okay, hopefully this is all fairly straightforward, but in anticipation of what will come next, let me just note that there's an alternative route to getting to the domain wall solution. This consists of just looking at the equation of motion for the scalar field, d squared phi by dx squared is equal to, let me just do the example we did before, g squared phi squared minus v squared, with particular boundary conditions that we chose already. And now if I interpret the x-coordinate as some effective time, you can see that this is just Newton's law for a particle with position phi moving in x time, but with a potential that is equal to minus of the original potential. Okay, these two maxima should of course be degenerate. And the domain wall solution exactly consists of the field configuration where my particle starts off at almost exactly or infinitesimally close to the first maxima of the potential, this inverted potential, rolls down, and as I go to large X, just reaches the second maxima where it stays. Maybe just in passing, let me mention a couple of other things, which is that actually I can work out an effective action for my domain wall solutions. This is given by minus sigma wall. So now in higher dimensions, the domain wall, as I said, doesn't have a mass. It has a mass per unit area. I'll call that the domain wall tension and call that sigma. And then integral d tau, d sigma, d rho, then root dead g. So here, tau, sigma, and rho are the world volume coordinates of the domain wall, and det g is the determinant of the induced metric. This is just something I'm briefly mentioning. We'll see similar effective actions for cosmic strings later, so it's useful to note that there's something similar for domain walls. In particular, this is valid when the thickness of the domain wall is small compared to the length scale of the physics that we're interested in. Let me also note that there's a bunch of interesting effects related to domain walls in the presence of fermions that I haven't been able to mention, things like charge fractionalization, similar things. Okay, good. Okay, any questions so far? Good. Yep. You need to have V very large compared to the scale of the physics. So you can also have, if you have spontaneous symmetry breaking at a high scale and you're interested in physics at low scales, this will be satisfied. I can have weakish coupling, large V, and the thickness will still be small compared to everything else. We'll see this in detail for the strings. So I think that we can. Okay, good. So just to get a feeling, who here, if I say the first homotopy group, knows what I mean? And this will also violate unitarity. Who doesn't? Okay, good, so some makes. So now I want to repeat this analysis, but for more general field configurations. For the domain wall, we had a particle-like field configuration in one spatial dimension. And then when we embedded that into 3 spatial dimensions, we get a domain wall, of course, or some sheet-like object. Similarly, if we have a field configuration that looks particle-like in d is equal to 2, this is going to become string-like. Or if we have a field configuration that, of course, is particle-like in d is equal to 3, or is particle-like in d is equal to 3. For d is equal to 1, spatial infinity was just 2 points. For d is equal to 2, spatial infinity is a circle. And for d is equal to 3, of course, it's a sphere. What we want to do is classify the boundary conditions that our real scalar or more general theory can have at spatial infinity, generalizing what we did for domain walls. And for this, we need a bit of topology. So a closed curve on some manifold M is just a map from the circle to the manifold. And we say that two curves are homotopically equivalent if I can continuously deform one into another. If you're a mathematician, you can make this all very precise, but your intuitive picture is actually fine and works well. So that curve is homotopically equivalent to that curve because I can just deform that into that. I then defined the set of equivalence classes under such deformations of these curves on the manifold M to be the first homotopy group. Let me... The best example of this is probably pi1 of the circle itself. So now if I consider the circle to be the manifold M, I want to know in what ways can I make closed curves on this circle that can be deformed into one another. Now clearly I can have a closed curve that just starts here, goes a bit here, goes back to the original point, and that I can deform down to a point. I could also start at the same point here, go all the way around here, go back forward, and so on, and end up back at the same point. But it's also easy to construct curves that start at some, let me say, base point, go all the way around the circle, and end up back where they started. Likewise, I could start at the same point, and then if I have such a curve, I could also do a curve that goes here, goes back a bit, goes forward, ends up back at the same point, and that could be then deformed into this previous curve that just went once around the circle. Likewise, I can have curves that go around the circle twice, minus one time, and so on in the opposite direction. So that means that pi1 of S1 is just the integers. You can probably also visualize that if I try to do the same thing with M being some sphere of some higher sphere, so Sk with k strictly greater than 1, then this homotopy group is trivial. All curves on a sphere can be contracted down to a point, or closed curves can be contracted to a point. Harder to visualize, but basically the same idea, is the higher homotopy groups, so pi n of M. These correspond to mappings from, instead of the circle onto the manifold, say a two sphere for pi2, or higher spheres for higher pi's. So it takes a bit more work to prove it, but you can prove that in general, pi n of Sn is equal to the integers is always true regardless of n. It's also true that pi2 of S1 is trivial. Now, one case that turns up often, also including in the standard model, is suppose I have some symmetry breaking pattern in my theory, that is some group G getting broken to an unbroken part H. Then the vacuum manifold of such a theory is actually given by the quotient space, G over H. Maybe for the sake of time, I won't define this precisely. If you haven't seen it before, feel free to ask me, and I'll explain it in detail. But an important result for actually some things of what I'll mention in the past is that if our original group is simple, compact, and also simply connected, then the second homotopy group of the quotient space is equal to the first homotopy group of the unbroken part. Now, with this mathematics set up, we can do topological solitons in detail in whatever space-time dimension we want. But before getting to explicit examples, we can actually derive some general theorem that will be useful or will at least give us some insights into what we might expect. So let me consider a theory just of scalar fields. Then, just like before, we can write the energy density of a static configuration as H is equal to integral over ddx. I won't bother writing out summations over the different scalar fields. You can imagine them. di phi squared plus some potential, now I'll call it v of phi. And just by shifting the potential, I can always impose that v of phi is greater than or equal to 0. So the first thing you can observe is that if we want some configuration with finite energy, then we're going to need that d phi of r, let me say r is the distance away from the origin, squared, must decrease faster than r to the minus d. Just so that this first term doesn't contribute infinite energy. Now, as a result, actually for d bigger than or equal to 2, the field phi must approach some constant value at spatial infinity if I want finite total energy. So if I imagine, say, the value of the field at this point at spatial infinity, and at this point, phi 2, and I look at how much difference I can have in the field between phi 1 and phi 2, then phi 1 as phi 2 is very schematically something like r times d phi. Given this condition that the spatial derivatives decrease fast enough, this is less than r to the 1 minus d over 2. So this would suggest that I can only have a single value at spatial infinity for my scalar fields, at least for d greater than or equal to 2. At this stage, you might think, well, we can just stop then. We've seen domain walls for d is equal to 1. We can't have anything interesting for d bigger than or equal to 2, so all we need to worry about is domain walls. Actually, there's already one get around from this theorem, which is like we saw in the axion case with n domain wall is equal to 1. I could have the field approaches a unique value at spatial infinity, but the field space itself has some structure that allows a non-trivial topology in the interior of the space. So given that there's that get around, let's see what else we can learn. So to do so, let's suppose that I did have such a field configuration that, and let me just assume that it solves the equations of motion. Let me call this phi s to be the solitonic field configuration. Then I consider some rescaled version of this field. So let me define phi lambda of x, where lambda is some parameter, to be equal to phi soliton of lambda x. So for example, if lambda is bigger than 1, this corresponds to compressing the field configuration. And now let me look at the energy of this rescaled field configuration. This is integral ddx, of course, half d phi lambda squared plus the potential of phi lambda. There's enough brackets. And then simply doing a change of variables, x prime is equal to lambda x. You see that this is equal to integral ddx lambda to the 2 minus d di phi lambda to the minus d. And after I've done this change of variables, x prime is equal to lambda x, all that I get back is the soliton field profile, but with these extra values of lambdas to the power of d. But now if we have that E lambda is less than the energy of our original field configuration, then clearly our solution isn't stable. We can just shrink it down and the energy of the system will go down. And in order to not have a situation where we can always make a lower energy configuration by picking lambda appropriately, the only option we have is that this term must scale differently to this term. And that is only possible if d is equal to 1. So again, we get led back to saying that we can only get topological solitons in space dimension d is equal to 1. Okay, so does this mean that domain walls are the only option? Well, definitely not. And there's various get-out clauses of this result, which is known as Derrick's theorem. One possibility is that we can have non-static field configurations. We'll see examples of this in the later lectures. Another possibility is we can have gauge fields. We'll see that very soon. We could also allow higher derivatives in our original theory. Then we'd get different scaling with lambda, get more possibilities. Actually, another option, which is cosmologically potentially relevant, is just give up on this requirement of finite total energy. So let us try to construct solutions in space dimension d is equal to 2, with the knowledge that probably we're going to end up somehow having to confront this theorem. So now let me fix d is equal to 2 and consider as theory of a single complex scalar. V phi is equal to lambda phi squared minus v squared squared. Now you all know what the vacuum manifold of this theory looks like. It's just a circle. M is equal to set of phi such that squared that's 1. And just as usual around the vacuum, we're going to write phi is equal to v plus, let me normalize it as h over root 2 e to the I chi. So the mass of the radial mode, mh, is 2 root lambda v m chi is equal to 0. And I'll sometimes use fa, which is equal to root 2 times v. Now the topology we have to consider is simply pi 1 example that we did earlier. So pi 1 of S1 in particular, which is equal to Z, which allows for topologically stable field configurations, and these correspond exactly to non-trivial winding at spatial infinity around the vacuum manifold. So if I have some loop in real space, sufficiently far from some point, when this loop gets mapped onto the vacuum manifold, I'll try to draw it but not super well, I will also do a loop in the field space. So let me use polar coordinates also for space. Then these solutions, or topologically non-trivial solutions, have the form phi is equal to f of r is the in theta z as I go arbitrarily far from the origin. I need f of r goes to the vacuum. And as I go towards the origin, I need that f of r goes to 0, because otherwise there would be infinite gradient energy. Remember, we're in d is equal to 2, so these look like point-like solutions where outside of this small region, I wind around the vacuum manifold. The core region of the soliton has size 1 over mr, and the potential energy associated to this region, V, is very roughly, well, its size 1 over mr, let me call it mh for consistency, mh squared times lambda v to the 4, which is exactly v squared. That's capital V. Okay. This is the potential energy associated to the core, but of course there's also gradient energy associated to the axion. I'll call the Goldstone boson here the axion, sometimes winding and having non-zero winding at all the way out to infinity. So the gradient energy is equal to integral dr 2 pi r 1 over r d phi by d theta. Let me put some large distance cutoff d here. So this is integral dr 2 pi v squared n over r. And as expected, we have some divergence in the energy density. This is equal to 2 pi v squared n squared mr over d to the minus 1. In fact, we knew this divergence was going to turn up just from Derrick's theorem. On the other hand, at least in cosmological settings, it's going to turn out that this divergence isn't fatal to our hopes of having interesting dynamics. Just like in the domain wall case, we can also define a topological current associated to this string, or this vortex solution, let me say. In this case, J mu looks like epsilon nu d nu phi star d rho phi. You can check, just like the domain wall case, this is identically conserved on all field configurations. And the associated charge Q is integral d squared x epsilon ij di phi star phi, which after a few lines of work is equal to integral over the circle at spatial infinity d theta phi star d theta phi which is just the winding number of the vortex solution. So how many times the field around this circle winds the vacuum manifold. Okay, this is good. It's established that the vortex solution is topologically stable. I think okay, for the sake of time, I think I'm going to skip the dual picture of how to describe these vortex solutions in 2 dimensions. There's some details in the lecture notes of how actually I can do some duality transformation and describe these vortices as particles that are charged under electromagnetism, or some fake version of electromagnetism. Instead, let me just jump to say kind of obvious things, that in d is equal to 3, I can construct the same type of solutions. Of course, these now become string-like. If I have some individual long straight string, then again, this will have a log divergent energy, but it's topologically stable. Just like for domain walls, I could have closed domain walls. Here I can also have closed loops of strings. These carry no topological charge. They can decay away, but they might be sufficiently long-lived to be interesting. And the key quantity that will be interesting for cosmology is the string tension, that is its energy per unit length. And that ends up being pi times Fa squared log of mr over d, where still I have to carry around this long distance cutoff d in order to render the energy finite. To anticipate what I'll say next time, in a cosmological setting, this distance d would either be the distance to the next closest string with opposite winding. So if you work out the details of this kind of field configuration with a string here, an anti-string here, at some point in between them, the gradient energy of the axion goes to 0 and this cuts off the divergence. Or for a string loop like that, the long distance cutoff would typically be of order its radius. Okay. Maybe one more thing to note is that two long straight strings with opposite orientation have an attractive force to each other. And actually this is a long range attractive force. It doesn't decrease exponentially like the domain wall one did. Okay. So let me now take the same theory as before, but introduce some gauge field. I'm going to gauge the U1 symmetry associated with the complex scalar. This will then evade Derrick's theorem, at least in the way that I wrote it before. So now my Lagrangian density is, just to set my conventions, 1 over 4 e squared f squared plus d mu phi squared minus lambda phi squared. And I'm using conventions that d mu is equal to d mu minus iq a mu with the gauge field. And let me say that this is just a U1. I'm just gauging the U1 symmetry, so I have f mu nu is equal to, just as usual, d mu a nu minus d nu a mu. Then, as I'm sure will be completely familiar, phi spontaneously breaks the U1 gauge symmetry. The vector gets a mass ma is equal to root 2 e times the charge of the scalar times its vacuum expectation value. mh is equal to 2 lambda v. And let me also work in the gauge where A0 is equal to 0. This still leaves time-independent gauge transformations unfixed, but that won't matter. And now the key point is that I can use this gauge field to cancel off the gradient energy that appeared in the global string case. In particular, let me choose a gauge field configuration AI is equal to n being the winding number of a string solution over Q, di theta, where theta is just the coordinate in space. So this is the same thing as minus n over Q epsilon ij xj over r squared. Then it's a small exercise to check that on exactly the same complex scalar field profile that I considered before, the covariant derivative d mu phi is equal to, let me just consider the spatial part since it's static and I've set a0 is equal to 0, di plus I n epsilon ij xj over r squared phi theta n. So here I'm considering the pure string, the simple string solution where I just have uniform winding from 0 to 2 pi. This is equal to 0. Moreover, if you work out the value of Fij associated to this gauge field, you can see that this is equal to minus n over q di epsilon j k k minus j k r squared. After a bit of algebra, is equal to 0 as well. And in combination, these two things tell me that for this vortex solution with the gauge symmetry, I have 0 energy density away from the string core, away from the vortex core. Another useful thing to note is that the winding number of this vortex solution, n, is equal to q over 2 pi, say, integral S1 AI dxi can be measured in terms of the gauge field around a large circle. Then using Stokes' theorem, this is just q over 2 pi integral d squared x f12. But f12 is exactly the magnetic field, so this is q over 2 pi squared x b, which tells me that a vortex carries magnetic fields through its core that is proportional to its winding number. So the properties of these vortices in practice depend a bit on the ratio between the gauge coupling E and the value of lambda. The case, yeah. Sorry. Good question. The magnetic field flux is quantized. Yeah. So this actually tells, this tells me that the string can only carry quantized magnetic field flux. The most analytically tractable case is when I tune, if you like, the gauge coupling E and the quartic coupling lambda to some special value, such that lambda is equal to E squared over 2. This is sometimes called the critical string or BPS string. And it means that the mass of the radial mode, h, is equal to the mass of the vector. Now, if I want to measure the mass of the vortex, or let's say the mass of the vortex, this is integral d squared x, 1 over 4 e squared, Fij, because it's static, plus mod di phi squared. And because it's a bit messy, I'm going to leave it as an exercise for you to show that in this special case, I can rewrite the vortex mass as integral d squared x, 1/2, 1 over e, the B field, plus E mod phi squared, V squared. That is all squared, then plus d1 plus d2 with an I, plus, just like in the case of the domain wall that we did right at the start, where we had a term depending on the boundary conditions, now I also get a term that looks like 2 pi v squared times the winding number. So, And I said it before, but just to emphasize, this simplification is only possible when that is true. Otherwise, you can't combine everything into this one term here. And just like for the domain wall case, we could use an expression of this form to find the field profile just from first order differential equations. We can do the same thing for strings here. So to find this string solution, or the lowest energy vortex string solution, we need to solve b plus e squared phi squared minus v squared is equal to 0. d1, d2, and in fact these are solutions that you can just solve directly. Usually on a computer is the most convenient way. For large values of r, we have that phi goes as 1 minus e to the minus mv r times v e to the in theta. And then inside the string core, we have phi going towards 0, and we have the gauge field, well, partially changing form as well. Another somewhat important thing that this expression tells us is that if I have two vortices in my system, then the combined energy of them, because each of them individually set these things equal to 0, is just given by the sum of their winding numbers. This means that the energy of the field configuration is the same regardless of whether the strings are far apart or close together, as long as they're not actively, well, even if they're overlapping, the energy is still just the sum of the energies. As a result, there's no long-range force between the strings. They're neither attractive nor repulsive for this critical case. In contrast, if I have say the mass of the radial mode is large compared to the mass of the vector, then I actually end up with something that has an inner core structure looking a bit like a global string, and then some outer region. Well, I have the very small inner core, at which the radial mode goes to the top of the potential. Then I have a global string-like part. Then I have a part outside that looks like a gauge string. And for two such strings, if they come within a distance where the global parts of their cores overlap, they have interactions just like global strings, whereas if they're further apart, they have no long-range interactions. You can also study the opposite regime where the mass of the vector is large compared to the mass of the radial mode. This is actually called a type 1 string. Again, for the sake of time, I'll skip this in detail, but I think in this case, the book by Weinberg has a very nice discussion. Okay. Let me instead talk about the effective theory of strings. So again, just like domain walls, I considered very briefly the limit where the domain wall thickness was small compared to the length scales of physics that we cared about. Let me do the same thing for strings. So I consider strings that are very thin compared to the length scales of the relevant dynamics. Then you can guess, and indeed it's been proven at least for these simple scalar field theory models that we've considered, that the action of the effective field theory of the string is simply the Lamborghini action. In some ways, there was nothing else that it could have been. So it's minus the tension, then integral d tau, integral d sigma, root again, det g. For local strings on sufficiently large scales, actually this is the end of the story. This is up to corrections that vanish in the limit of infinitesimally thin strings, just the action of the string. In the case of a global string, it's more interesting because we have this light degree of freedom, the Goldstone boson or the axion, which needs to be included in our effective theory. The way to do this is actually to introduce some tensor f mu sigma, let me call it. This is not some gauge thing, it's actually just some trick to parameterize the value of the axion. So by definition, this is d mu A nu sigma plus d nu A sigma mu plus d sigma A mu nu. And now I make the identification, which will turn out to be a good choice. F mu nu rho is equal to epsilon mu nu rho sigma. Yep, the indices match. D sigma A over root 2. Why have I done this? Well, in some ways it's a good choice because first of all I can write the axion kinetic term as sigma, that works, sigma. Another thing to note is that the accretional motion of the axion, which is just that is automatically satisfied if I define f this way. This just corresponds to d mu f mu nu rho is equal to 0, which is identical. And in some ways, the real reason for going through this work of mapping the axion onto this object f is so that I can couple the axion to the string in a way that is, let's say, regular at the string core. In fact, the interaction takes the form of a Karl-Bremond interaction. So I have minus 2 pi fa, n is the winding number, and actually there turns out to be a factor of root 2 here. Integral d tau, integral d sigma, epsilon ab, dA x mu, x nu, x. So for anyone who is a string theorist, this will look familiar. For people who aren't, the picture here is that if I consider my 3D theory, I have my string. As it moves in time, it traces out some world sheet. I parameterize this world sheet by tau and sigma. So let me say tau that way, sigma along the string, such that these x mu are the target space coordinates, so they tell me for a given value of sigma and tau where in the universe the string is. Then once I've got this description, I've got the right index structure to couple it to A mu nu, which is the thing that is related to f, which is the thing related to the axion. And indeed, it's been proven that this, at least for the simple global string example I wrote, that this is actually the effective theory of the string. Again, somehow, like the Nambu-Goto action was the only thing you could really plausibly get out, it's kind of plausible that this is the only way you could think to couple an axion to a string. This coupling constant here is fixed by demanding that the axion field has the right behavior around a single string. Oops. Okay, let me also mention a case that is going to be cosmologically relevant, which is some system where I have both strings and domain walls. This is going to be slightly schematic, but let me write V is equal to lambda mod phi squared minus, let me write in terms of FA squared over 2 squared. So here I'm thinking of a complex scalar field with the usual spontaneous symmetry breaking like we did before, just a global symmetry. But I'm also imagining, and I'm imagining this happens at some high scale FA that is much larger than the axion mass, which is the mass of the Goldstone boson. So if you like, I have my usual symmetry breaking. And as I go down to lower energies, first of all, I break the U1 symmetry. And then around the bottom of this potential, I put in a tilt that is very small compared to this overall magnitude v to the 4, but gives the Goldstone boson a small mass. So what do the topological defects look like in this case? Well, first of all, I certainly have strings associated to this breaking. These are going to have tension FA squared. I won't worry about factors of pi times some log of MR over my distance cutoff. But then also associated to this small potential for the axion, the degree of freedom in this direction, I'm going to have domain walls, and these will have tension. Mu's of order axion mass times FA squared. Of course, the tension of a domain wall is an energy per unit area. The tension of a string is an energy per unit length, so they have different dimensions here. But now if I look at a long string solution, well, you know that as I go around the string, I'm winding around the bottom of the potential. That means I will also see this potential for the axion. So if I have a long string, then it will necessarily be connected to domain walls. This is probably the limit of my artistic ability, but if you, in particular, as I go all the way around, I'm going to pick up n wall, different domain walls. One here, and so on. Additionally, if I have a loop of string, then this will also necessarily bound a domain wall inside it. And there can also be topologically trivial domain walls which actually aren't connected to strings. So strings are necessarily connected to domain walls, but not vice versa. This may be harder to draw, but if I imagine some bubble of domain wall, then actually it doesn't need to know anything about the UV completion or the high energy completion of this theory. It can just be a domain wall by itself. Okay, finally, let me just very briefly mention that just like with domain walls, I've skipped over a bunch of other interesting possibilities. I can have superconducting strings. If I have fermions in my theory, then I can have massless fermion modes that live on the string. This has, again, subtle connections to anomalies, things like that. Actually, also, strings have interesting gravitational effects. In particular, the space-time around a string is locally conical. So actually, for an observer who looks only locally around a string, space-time looks flat. But if an observer does an entire loop around the string, they'll notice that the geometry is missing an amount. It's called the deficit angle, delta theta, which is 8 pi g Newton times the string tension. And actually this leads to some of the observational signals of cosmic strings that we'll see next time. Okay, so unfortunately there's no time for monopoles. They won't be essential for what follows, but if you're interested in monopoles, then yeah, please read the lecture notes, and happy to discuss them afterwards anyway. But I think that is my time up, so I'll stop here.